Hey everybody, welcome back to Tuesday, and we are going to be looking at how do you make potions or solutions in Chem 20. And there's two parts to today's lesson. One of them is learning the techniques that you need, the glassware, the procedures, and then the other is the math, the calculations. Your goal by the end of today's lesson is to know the steps needed to build an exact solution that has a known concentration and an accurate volume. So that's the goal today. And as you can see from our lovely little graphic here, we've got Professor Snape, our potions master at Hogwarts. And today you guys will be making Muggle solutions. Same techniques, but no magic. Okay, you've probably never seen this special container before. I'll just draw the outline of it. Okay. These are special pieces of glassware called volumetric flasks, and you're going to learn how to use those today and why they're so important in building standard solutions. Okay, so first thing in your notes is you need to put down the definition for a standard solution. A solution prepared with an accurate and known concentration. So in order to have an accurate and known concentration, it usually has to have an exact mass and volume. So that's what you're going to be doing today, is figuring out exact masses and volumes. So that's the goal. Okay, so first thing I'm going to do is just show you the math. We're going to do two questions with the math pattern. So I'm just going to show you one right off the bat. And the question is, what mass of KMnO4 is needed to make a standard solution? So that's that solution with a known and a known accurate concentration. So the solution is going to be exactly 100.00 milliliters. Okay, that is a very precisely measured volume. Okay, and a very accurate known concentration of 0.00400 mole per liter. So how do we do that? Okay, I'm just going to flip my laptop around here. Okay, so we're looking for the mass of KMnO4 that's needed. So our units are going to be grams. So when I look at this question, where do I get grams from? I've got milliliters and moles per liter, no grams. So usually in chemistry, it's a pretty safe bet that if you're looking for grams of something and it's not given in the equation, you need to get the molar mass. So the molar mass of KMnO4. So I've already looked this up. It's 39.10 grams per mole for potassium. Manganese is 54.94 grams per mole. Oxygen is 16 times 4. We add all that up, we get 158.04 grams per mole. Okay, so we're going to figure this out using unit analysis. So we want grams, and here is our grams. So we're going to leave it the way it is and make sure that that grams is on top. 158.04 grams per mole. Okay, so there's our mass of KMnO4. We just have to get rid of moles. We can get rid of moles using this unit. So I want the moles on top. 0.0400 moles over liter. Okay, moles cancel out. Perfect. Now I just have to get rid of this liters. So I'm going to put a liters on top. Where do I get it from? Right there. 100 milliliters is the same as 0.10000 liters. We're going to maintain the sig digs. This number has 5 sig digs and this number has 5 sig digs. So when we convert, we don't lose our significant digits. Okay. 100 milliliters divided by 1,000 is, so that's 1,000 milliliters per liter, and there we go. Okay, liters cancel out. Liters are gone. So multiply all those together and you get 0.0632 grams. Let's check our sig digs. So we've got 5 here, 3 here, so there's our 5, there's our 3, and here's 5. So we go with the lowest number of sig digs, 3. So that number is correct. Okay, so if I want to make a standard solution of this volume and this concentration, I need this mass of KMnO4. So then the question is, okay, well, how do I actually make this thing? I've measured out 0.0632 grams of KMnO4. How do I turn that into this standard solution that I'm looking for? So here's where the lab techniques come in. You need to choose the appropriate tool for the job. I'm sure you've heard your mom or dad say this before. When you're going to build something, make sure you have the right tool for the job. So to build our solution, we need the correct tool. So we need a volume of 100.00 milliliters. So my question for you is, which of these tools would be the best? And I'm going to assume you know the names of some of these. This one you should all know, beaker. And you should all know this guy. I'm just going to put its initials, GC, graduated cylinder. And these guys are GP, graduated pipette. Why are they called graduated? Graduated is plural for graduations. Graduation means a level or a mark. Our grade 12s will reach a level or a mark of completing high school, so they will have graduated. So these all have graduations or lines or levels on them. It allows us to measure multiple volumes. The last one you've probably never seen before, so I'll put down the initials, VP, VF. What do you think the V stands for? If you said volumetric, you are wrong. I'm kidding, you're right. Volumetric pipette, volumetric flask. So these tools are specialized. They are only used to measure one volume. They have a mark on them for only one volume. This one measures 250 mil. This one measures 25 mil. That's it, nothing else. Okay, now let's take a look at the level of accuracy of these things. If I asked you to measure 100.00 milliliters using a beaker, you would be able to get within 5 mils. So for example, you might get 95 to 105. You get within 5 mils of what I'm asking you for, but I want this level of accuracy. A graduated cylinder gets you within 1 mil, so I could get between 99 and 101. And you can see these examples down here. So that's not good enough either. Graduated pipettes go within 0.1. So now I could get down to 100.1 to 100.3. Still not good enough. I want to the 100th of a decimal place, and that's where the volumetric flasks come in. They measure plus or minus 1/100th of a milliliter. So now I could get down to 100.01 to 100.00. So I'm getting really close to that level of accuracy that I'm looking for. And that's reflected in these examples underneath. So you might want to jot that down in your notes, pause the video, and just put those examples in. Choosing the right tool for the job. Beakers are good for mixing and heating. They're more like a bowl. If you're thinking of cooking in the kitchen, this is your mixing, heating bowl to put in the microwave. And a graduated cylinder is like a measuring cup, and a volumetric flask is a whole nother level of accuracy that we don't use in our kitchens because we don't need to be that accurate. Okay, so now that you know the right tool for the job, VPVF, let's go on and take a look at the job. How do you build these solutions? Okay, the method's pretty simple. Weigh your solid. So for the example that we just did, it was 0.0632 grams. So once we've got that solid, we take our volumetric flask and we bring it about half full with distilled water. So a third to a half full with distilled water. Then we're going to add our solid and dissolve. Stir until dissolved. Now this is using a magnetic stirrer. We don't use those in our high school lab. You're just going to stir by swirling. Swirl, swirl, swirl. Get all of the solid or solute to dissolve in the water. Once it's dissolved, we're going to add more distilled water to bring it up to the mark. And if I could zoom in on that, the mark would be the bottom of the meniscus. I'll show you an example on this slide. No, this slide. So here's an example of measuring in a graduated cylinder. So if you're looking at this graduated cylinder and I asked you, what's the volume? You'd go, okay, well, it's not 20. It's not 21. It's not 22. It's in between 21 and 22. So we could zoom in even more. And now we're looking at the meniscus. So the bottom of the meniscus, what's hidden behind my picture there, make a reading here. So you read at the bottom of the meniscus. So 21, 22. If you guys had to predict, what do you think the volume would be on this one? 21 point, is it past halfway? I think so. So 21.6 or 21.7. 21.6 or 21.7. On this one, you are bringing that meniscus down to the line. That's not a very good drawing. I'm going to draw it even better for you. Okay, let's put our line like that, and our meniscus of water will dip down. So I've overflowed that one slightly. I would want the water, the bottom of the red meniscus to just touch the black line. And at that point, it would be exactly 100.0 mil. And if you were using a graduated cylinder, you couldn't be that accurate. You'd be guessing and you'd be 21.6, 21.7. But on this one, we have that much higher level of accuracy, and you are in control of that because you are adding the water drop by drop by drop until you hit the line. And hopefully you don't overshoot it like I did on that example. Okay, so that's the technique to build a standard solution. You've seen the math and you've seen the steps needed. So let's do one more example in your notes, and we'll move on to the second part. What mass of solid copper 2 sulfate pentahydrate is needed to prepare 100 milliliters, 100.00 mil of 0.300 mole per liter? Okay, copper 2 sulfate pentahydrate. Copper 2 is copper 2 plus. Sulfate is SO4 2 minus. So copper sulfate, penta means 5 waters, pentahydrate. Okay, that's a huge molar mass. 1 copper, 1 sulfur, 4 oxygen, 10 hydrogens, and 5 more oxygens. Add all that up, you get a molar mass of CuSO4 5H2O equal to 249.72 grams per mole. And remember, we need that molar mass because that's where we're getting our grams from. So what mass do we need? 249.72 grams per mole. Okay. If you want to finish off the calculation, you can pause the video here and go ahead and do it and then come back. Okay, we need to get rid of our moles. 0.300 moles on top, liters on bottom. Okay, moles are gone. Now we just need to get rid of liters, and that's that 100 milliliters or 0.1000 liters. Gone. And crunch all those numbers, you get 7.49 grams. It's written right on the screen. 3 sig digs because that's 3 sig digs. Okay, so to build it, you are going to take 7.49 grams that you've weighed out. You are going to add it to this volumetric flask that's half full of water, get it to dissolve, and then bring it up to volume. And there you can see, not easily, the line. Oh, look, there it is. Amazing. Okay, so that's how you would make a standard solution. I do have a video as well that goes through this, and I'm going to put the link in here. It's this guy. Oh dear, that's not the button I wanted. Okay, let's try that again.
You want to be a more successful chemist or just a more successful chemistry student, you have to know how to be able to prepare a standard solution. That is, a solution of known concentration. And there's two ways that we can go about preparing this standard solution. One is from a solid, that is, we can take a known solute and dissolve it in a certain amount of solvent, in most cases water, to prepare our standard solution. Or we can take a solution of known concentration and add more solvent to it to create a less concentrated solution. This is a process that we refer to as a dilution. And we're going to take a look at both methods of preparing a standard solution.
Okay, so as he mentioned, you're going to look at standard solutions, which we've done, and he's also going to go through dilution, and that's the second part of our lesson. So I'm going to go through that one with you pretty quickly here, and then we are done. So you can prepare a standard solution from a solid, or you can prepare it from a concentrated stock solution. So why do we have concentrated solutions? Well, often concentrated solutions are sold because they're cheaper for shipping. They take up less volume, less space, which means if you have a smaller container, you're saving on money and you're saving on storage. Hey, you're even saving on the environment. Anytime you can ship less volume, it's cheaper, less gas, it's better for everything. So why do we dilute substances? Well, we always start with concentrated to save money. And then in the lab, we often work with dilute. And the reason we work with dilute is mostly for safety. Okay, if we can do the job with a dilute solution, there's less chance of poisoning. There's less chance of corrosive burns for acids and bases. So there's a safety component to that. Okay, so how do you do a dilution? Start with a stock solution. This is one that was purchased. It's usually a standard of a known concentration and volume. And then to dilute, you're going to add a solvent and bring it to a desired volume. And the solvent is always going to be, guess what DH2O stands for? Distilled water. Good. Okay, so how do you do that? You're going to use a formula. One of the very few formulas that we use. This kind of looks like Boyle's law. Remember P1V1 equals P2V2? This one is C1V1 equals C2V2. Guess what C stands for? If you guessed cure, you're wrong. If you guessed concentration, you are correct. And V stands for volume. So concentration 1, volume 1, concentration 2, volume 2. All right. So there's a formula. It's pretty simple. Works just like Boyle's law. Okay, so we're going to go through the math, but first let's talk about the technique. How to make a dilution. So you're going to use a VP, volumetric pipette. And you're going to measure a small amount of the stock solution. That's the concentrated one. And usually in the high school lab, it's 10 mil, but not always. It could be 5. This example is 10. And because it's a volumetric pipette, we get that extra level of accuracy, 2 decimal places. And you can see the line on the volumetric pipette right there. So it measures exactly 10.00 mil. So we pipette 10 mil. Add it to a volumetric flask with our new volume. So this is, I guess I should write here, volume 1. This will be volume 2. And usually, but not always, we make solutions of 100.00 mil. So volume 1 goes into the larger flask, volume 2. We then add the DH2O and dilute it. Distilled water is added until the meniscus is reached at the line and we have our exact volume, 100.00. And this is now concentration number 2 that we have calculated. So this would be our new standard solution. Right now, some of you are thinking, this is so fascinating. I could just sit and listen to him talk about concentrated and standard solutions all day long. I know, it's crazy. It's crazy. The sad part about this is it's actually kind of fun to go out and build these in the lab, and it sucks for all of us that we don't have that option. So next year, when you're taking Chem 30, you'll be able to build these solutions in our lab when we're all back in school in the fall. Okay, last example, the math. How do you do the calculations? Okay, so we have our formula. So the key here is you're reading a question and you go, oh, we're starting with a stock solution. Sometimes it might even say dilute or dilution. So when you read the words dilute, dilution, or stock solution, or you see two concentrations, here's a concentration and there's a new concentration, first thing you should do is write down the dilution formula. DILU. I figured out why my pen is so slow on these, because this file is huge memory, so it just slows this little Chromebook down and it can't keep up with my speed of printing. Everything is paused. Okay, so what have we got here? We've got 100 milliliters at 0.03 mole per liter. So we're going to call this volume 1 and concentration 1. Just like Boyle's law, the important thing is that these two go together. I could call them volume. So this is volume 1, concentration 1, or I could call them V2, C2. But the important thing is they belong together. They're both 1s or they're both 2s. This is our new concentration, so we'll call that one C2. So the question is, what is volume 2? So rearrange and solve for volume 2. C1 over V1. Sorry, C1 V1 divided by C2 equals V2. Okay, C1 V1. 100 milliliters, volume 1 times concentration 1 divided by concentration 2. Moles per liter cancel out. We're left with liters, and you get 10 milliliters, and it's actually 3 sig digs, so 10.0 milliliters. Okay, so to build this solution, you're going to need to pipette 10 milliliters of stock solution into a 100 ml volumetric flask. So pipette 10 mils of stock solution into a 100 ml volumetric flask right there. Ugh, I need to get smaller files. This is crazy. Okay, that's the math, that's the techniques, that's everything you need to know. There's one page to do in your study guide, page 194 for Johnson, page 198 for Kelly. Questions 1 to 6. This is optional. There are some good questions in here on techniques if you'd like to review that. I'm also going to throw that video. It's, I think, 6 minutes long, and he goes through how to build the solutions as well. If you'd like to see the equipment being used and the steps, I recommend it. Okay, that's it. We're going to stop there. Have a great day, everybody, and I'll see you guys tomorrow.